Hi there, thanks for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. Coming up, we're going to do some homework. Gus sent us a question a couple of weeks ago. It was so convoluted and complicated, he gave up. But we'll revisit that because he's actually come up with something very interesting. You might not have realised that. We'll also be looking for the sun's dark matter twin, according to Rich. Other questions involving time dilation and dead stars have been sent to us. And a question we've done before, we will revisit because Fred likes Anthony's accent. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Here he is once again to answer all of those questions and more. Professor Fred Watson, astronomer at large. Hi, Fred.
Let's start on an optimistic note that maybe we can answer some of them.
Yes. Well, at least we have a homework department that can. We can always go back to them later, which is what we're going to do today. Shall we just get stuck straight in?
I think we ought to, yes.
All right. So our first job today is to answer some homework from Gus, who sent in this question a few weeks ago.
Hello, Professor Fred and Andrew. This is Gus Iverson from Issaquah, Washington. I sent in a question for you guys previously, and you thought I was in Western Australia. I've been thinking about gravity today, and it came to my mind that if energy and mass are equivalent, then essentially shouldn't energy also create gravity at some level? I'm not sure if this is a related question or an extension or a separate question, though. Additionally, if a body of any size is generating or has mass and it is generating a gravitational field, does not that field itself have energy and mass? And would that field not create additional gravity by its simple existence? So if that's the case, or even kind of the case, my question is, where does the energy and mass go I have no idea where to go with it. Thank you. I love the show and appreciate being able to ask questions.
Thank you, Gus. Yeah, he ran out of puff, but we put this one on the back burner because there was a lot going on there, a lot of thinking, and Fred's done the homework, and you've come up with an answer. In fact, you've suggested before we started that Gus might have been onto something.
Yeah, I think he's doing pretty well with that sort of thinking. We did talk. I think we covered part of this a little while ago. We spoke about if you've got a planet and you increase its temperature by 200 degrees Celsius or something, that actually contributes to its mass because you're putting energy in, and so it would affect its gravitational pull. But the nub of, I think, Gus's question comes down to the issue of whether the hypothetical particles, which we haven't yet detected, and there is no theory to support them, but they are still doing the rounds, the hypothetical particles of gravity, which we call gravitons, I guess analogous to the fact that we call particles of light, photons, which are certainly not hypothetical. We know a lot about them, and they certainly exist. They're definitely part of our big picture of the subatomic world. But gravitons aren't yet, but they are thought to exist, so that because gravity is one of the four fundamental forces of nature, all the others have particles associated with them, and so we expect gravity to as well. And eventually, we will probably be able to prove that gravitons exist and that they, that they are real, and that we can see evidence of them. The issue that Gus postulates, though, boils down to, do gravitons themselves have mass? And the assumption has always been, and this is because effectively that's what Einstein's relativity predicts, although it doesn't really talk about gravitons, but the assumption has always been that gravitons are like photons, massless particles. They don't have a rest mass. That's the way to put it. So photons, we know, don't have a rest mass. Gravitons are assumed not to have a rest mass either. But there is science that's going on. People are researching this. And in fact, I'm reading an article which is easy to find. It's on the Guardian's website. It's actually 4 years old now, 4.5 years old. But it's about the work of one particular physicist whose name is Claudia de Ram, who's at Imperial College in London. And she has built a theory that postulates that gravitons have mass. And if they do, then they've got intriguing consequences. And one of them is that they would have, if they do have mass, then it would mean that their influence on very large distances, on very large scales, is weaker. And that could account for the phenomenon that we see of the acceleration of the universe, the accelerated expansion of the universe. In other words, what we call dark energy. If you have mass, gravitons with mass, then that could explain the accelerated expansion of the universe. Fantastic thing. Wow. That would solve so many problems. However, and I'm going to quote from the Guardian article here because I love this. This theory, what it says is, despite successive efforts, previous versions of the theory had the unfortunate feature of predicting the instantaneous decay of every particle in the universe. So there's a drawback to it.
Okay.
And a quote from Claudia de Ram: very clever people had worked on this and the arguments were very compelling. People thought it would be impossible to make it work. But there was a paper published back in 2011 which had a pretty hostile response from the scientific world. In other words, people saying, this is all ridiculous. It doesn't work. It means every particle in the universe decays instantaneously. So it's still a work in progress.
Yeah.
But the reason why it was in the news back in 2020 is that Claudia de Ram was the recipient of a $100,000 US Blavatnik Award for young scientists. And it's one of, it's an award that is put in a place where people think the research is actually going to bear some fruit. She actually won the Adams Prize as well, which is a Cambridge University very prestigious award. So it's still a theory. Massive gravity is still a theory, but has attractive features. I mean, if you can explain away the accelerated expansion of the universe by having massive gravitons, that is brilliant. But especially if you can do it without everything else in the universe decaying. So it's interesting. And one of the other aspects is that you might be able to detect this by fairly subtle ways using gravitational wave detectors. And as they become more and more, more and more refined, and I guess the gold standard is going to be LISA, what's it called? Large Interferometric Space. I can't remember what the A stands for, but it's an ESA project to have a space-based gravitational wave observatory. It's if something like that had the sensitivity that we expect it to have, then it may well be that we can one day say, well, gravitons have mass, and that would revolutionize our whole thinking about the universe. So, Gus, you've done very well there in putting an idea, even though you ran out of steam, as I would have done where you were in the thinking. It's got some credibility.
Laser interferometer space antenna.
That's it, antenna. That was the word I'm looking for. Thank you.
Your answer to Gus's question is going to probably result in someone asking another question, which might be, okay, we don't know that gravitons exist, or we just assume it. We haven't identified them yet. But could gravitons be dark matter? Or dark energy, for that matter.
Well, yeah, that's what they're saying. They're saying there's no need for dark energy. If you've got massive gravitons and they weaken, their effect weakens over distance, so you don't need dark energy because basically the gravitational pull of everything in the universe is weaker than we think it is, and that could explain the accelerated expansion. Dark matter. It's an interesting thought. Except dark matter is something that's associated with normal matter. I think I've got to think about that one a bit more. So there's more homework from you, Andrew.
Sorry about that.
That's all right.
Okay, thank you, Gus. We finally got there. While we're talking about dark matter, here's a question from Rich in the UK. Hi, both, and Hugh in the studio. Great show, such a broad spectrum of information. You do a great job. Okay. My question harks back to a number of different episodes where you've talked about the theory of our sun may have been born of a twin, Planet 9 roaming about somewhere in there, and that dark matter is only measurable by its gravitational effects. So I put 2 and 2 together and came up with 13.7. Is there any plausibility in the idea that the sun has a dark matter twin somewhere in the vicinity that could be demonstrating the effects we see on our solar system instead of a Planet 9? Rich from the UK, or maybe it's a town called Uck. I'm not sure.
No, it's not Uck. It's So interesting idea. I mean, we've got no evidence of dark matter entities.
Stars.
Yes, stars for a start, planets for a second. And in fact, it was experiments done in the 1990s, some of which were done here in Australia, that ruled out the possibility of there being lots of dark matter objects, which we call black holes, basically. It ruled out, that dark matter was dense stars, in other words, what we call black dwarfs, or rogue planets, or black holes that we hadn't detected, because they would have a signature on the stars beyond them. They'd have a gravitational lensing signature. And I think that would be the same if you had a dark matter planet. It would have a gravitational lensing signature, and nothing's been observed so far. It's true, though, that some people have suggested that perhaps Planet 9 isn't a planet. Perhaps it is a black hole, a tiny mass black hole, something much smaller than a star, which would suggest that it was a primordial black hole, one that was created in the Big Bang, not by the collapse of a star. So these are ideas I think that are floating through the astronomical community as well. So you're not thinking that far out of the box, except a dark matter planet is something that I don't think mainstream astronomy thinks could exist. So that might not be the exact answer. But thank you, Rich.
Yeah. Yes, very good. Thank you, Rich. This is Space Nuts. Andrew Dunkley here with Professor Fred. Let's take a little break from the show to tell you about our sponsor, Incogni. Now, if you use the internet, chances are you've registered your name, your address, your phone number, your credit card details on one or more or many websites. Occasionally, those websites will get infiltrated and that data gets sold on the dark web. And there was a case recently where 13 million people most likely had their medical data sold through the dark web, 13 million. Now, what happens to that data? Well, it could be just about anything. Data is a valuable commodity these days. It's used to create fake IDs. It's used to enable people to make spam phone calls and spam emails. It can lead to you being scammed. There was a famous case only recently where somebody got a call from their bank, and it was so convincing they gave them information which led to them losing tens of thousands of dollars. And the bank won't pay up because they voluntarily gave the information out. It's a very nasty case. But this is what happens. So what do you do about it? Well, you can go in and clean it up yourself, but as fast as you do it, some other organisation or individual has already taken your data and sold it again. It's estimated it would take you probably 2 years to wipe the internet of all your personal information if you went it alone, if you knew how to. So probably better to get someone to do it for you. The solution is simple. You sign up to Incogni, and they will do all the hard work for you. They'll clear all your personal data from the World Wide Web, and they'll keep cleaning it up in an ongoing fashion. All you have to do is sign up, fill out a bit of background information, give them permission to work on your behalf, and then you just go from there. And it's simple, it's inexpensive, and it gives you peace of mind knowing that your personal information cannot be corrupted or stolen or sold on the web through Incogni. So how do you do this? Well, as a Space Nuts listener, you get a special deal. Just go to incogni.com/spacenuts. That's incogni.com/spacenuts. There is a special deal on at the moment, 60% discount, and that will enable Incogni on your behalf to limit public access to your private info and reduce that risk of identity theft significantly and keep your data from being sold. And that's what it's all about. There are several options in terms of subscriptions as an individual, or you can do it as a family and friends plan. Each plan varies in price, but if you pay for an annual plan up front, it really drops the price significantly over the course of a year. But if you want to pay month by month, you can do that too. And don't forget, it comes with a 30-day money-back guarantee. A 30-day money-back guarantee. All you have to do is log in, create an account, and sign up for whatever deal suits you at incogni.com/spacenuts. And don't forget the coupon word Space Nuts, surprisingly. So that's incogni.com/spacenuts and the coupon code Space Nuts. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our next question comes from Sean. There seems to be controversy surrounding the James Webb Space Telescope's pictures of galaxies in the early universe and how many of them seem to be too big and well-formed when they're only 500 million or less years old. I was pondering this question over coffee this morning. People tend to do that, and was wondering if time dilation might have anything to do with this. It seems to me that if the early universe was expanding at anywhere near light speed, from our point of observation 13.8 billion years in the future, things wouldn't be what they seem. You guys are the best. I hope this question can provide a few moments of filler to your awesome podcast. Sean from British Columbia.
Sean, you underestimate yourself. It's far more than filler. This is interesting stuff.
This is
None
deep.
of our questions are fillers. I mean, time dilation's an interesting aspect of our view of cosmology. I don't think it solves the problem in this case, but partly because what you're talking about, Sean, here is relativistic time dilation from special relativity. You're talking about it from the point of view of things moving at near relativistic speeds, in other words, near the speed of light. Yes, you're right that the early universe expanded probably faster than the speed of light, but only for about 10 to the minus 33 of a second. So this was way, way before the origin of galaxies, way, way before the origin of, well, matter, actually, because it was just pure energy at that stage. And since then, the expansion has been much more sedate. So the speeds involved are not such as to, I hope I'm saying the right thing here, to be relativistically significant. In other words, they wouldn't cause time dilation of the kind that you're thinking of. In other words, the idea that we're looking back, or our look back time is illusory. That's the point that I think you're making, that we think we're looking back in time to a time, when the universe was only half a billion years old, but we're not. We're actually, that's an illusion. We're looking back to a time later than that, and I don't think it works in that situation. It's a nice thought. Time dilation is always good to think about because it's such a spooky phenomenon, but I don't think it works in this case. Far more than a filler, Sean. A great question. Thank you very much.
Indeed. Thanks, Sean. And a question from Jane. How many stars in the humanly observable universe are already dead?
Yes. Well, the slow... I can't give an answer to this, but I can waffle on about it. The rapid, or the brief lifetimes of very massive stars, they are only 10 million years or less for a very massive star, such as we think were created in the early universe. These are, live fast, die young stars. They're what makes the spiral arms of galaxies look blue. These are young stars, massive stars that aren't going to last very long. They'll detonate with a supernova, possibly forming a black hole very quickly. So there's lots of those stars that are already dead because they're now something else. Yeah. The most numerous stars are in the vicinity of the sun in our own galaxy are red dwarf stars, and they're very old, and they'll go on being very old because they're the opposite of these, live fast, die young, bright, supermassive stars. They're low mass. They churn through their hydrogen fuel very slowly and last for billions of years, outlasting the sun. The sun's got a lifetime of about 10 billion years. These red dwarfs will go on much longer than that. So there's a lot of those stars that aren't dead yet. But at the same time, there are a lot of stars that are that are dead too. So, Jane, I can't give you an answer to that question directly, but to say that, yes, there is a population of objects in the universe that are no longer visible because they've turned into something else, either a black hole or a white dwarf, as a sun-like star would turn into. It's one that I'll think about again a bit more. I'm not going to call it homework because I might forget, but I'll think about that a bit more and see if we can come up with a number. How many stars in the humanly observable universe are already dead?
It'd have to be in the billions, wouldn't it?
Well, absolutely. So how many stars are there in the universe? About 10 to the 23, because there's something like 10 to the 11 stars in a galaxy, and there's about 10 to the 12 galaxies in the universe. So that makes 10 to the 23 stars. And they're stars like those in our own galaxy, but that doesn't account for the ones that might have already popped off as supernovae. So it would be billions. It might actually be more than billions.
It's a lot.
A lot. A technical answer is a lot. Yes.
A lot. Thank you, Jane. Lovely to hear from you, and nice to get a question from our female audience sector. That's very official, isn't it?
It's the only way you can say it these days, Andrew.
Yeah, I was trying to be careful.
I know. Well done.
Finally, we're going to revisit a question we've had before. This is from Anthony, and the reason we're doing it again, Fred likes Anthony's accent. No, I'm not kidding. That's the truth.
Hi guys, Anthony here from Kilkenny in Ireland. I've been looking at absolute zero being minus 270 odd degrees Celsius. And if there's an absolute zero, surely there must be an absolute high temperature. Could you tell me what that is? Thank you.
To be sure.
I've just realised.
What a great accent.
Isn't it lovely? Yeah. So, sorry.
Anthony,
yes, right. Going back to Sean, because that's a very Irish name. Anthony's from Kilkenny. Here's a weird thing, Andrew, a little weird coincidence. The friend of mine that I mentioned who was reading Dune back in 1967.
Yep.
His name is David Kilkenny.
Oh, no.
Yeah, there you go. Closing the loop there. Just a little strange coincidence. I'm sure Dave doesn't listen to the Space Nuts, but if you do, Dave, how are you doing? Time you wrote to me again. He lives in Cape Town in South Africa. When I came to Australia to make my career back in the day, he went to South Africa to make his career.
Here's another coincidence, Fred.
Yeah.
Quite a shocking one. I don't know if you've heard of the cartoon series called South Park.
Yes.
But in every episode, they kill Kenny.
Oh, there you go.
Oh, dear.
I don't know where else this is going to go to, but let's go.
What was
to
the question? Absolute zero. What's absolute maximum? Now, we did have this before, and we did answer it. Not, if I recall correctly, the answer is there isn't one. Is that what happened?
Yes, it is. That's correct. So absolute zero is defined. So temperature is the effect of particles moving. In a solid, they just vibrate. So, the fact that my desk is getting a bit warm because the heat is pointing at it means that the atoms in the desktop are vibrating. In a liquid, they swirl around. In a gas, they zoom about all over the place. The temperature is related to motion. And absolute zero is defined basically as the temperature at which all motion stops. So there isn't an absolute maximum because things can move as fast as you want them to, especially in the rarefied gas between the stars and planets. But absolute zero is well defined. It's the temperature at which atomic motion stops, and it's, as Anthony said, minus 273 degrees, minus 273 degrees Celsius.
There you go. That's cool. Yeah, it's been like that here lately, though.
Yeah.
All motion stopped in my case.
All motion stopped, that's right. Well, there you go.
Especially on the golf course. Gosh, it's been bitterly cold out there. We must be idiots. But most golfers are. Golfers and fishermen. Yeah. Go out in all sorts of weather. So there is no absolute maximum, Anthony, is what we took a long time to say. But thanks for the question and love the accent. That's just about it. Don't forget, if you've got questions for us, you can send them through for our Q&A episodes via our website, spacenutspodcast.com or spacenuts.io. If you click on the little AMA button up the top, it'll give you an interface to send us text questions, or you can send an audio question. But on the right-hand side of the homepage, send us your questions. Press that and you can send us an audio question. Don't forget to tell us who you are and where you're from. Fred, thank you so much. It's been a great pleasure as always.
Good to chat, Andrew. I still wonder how we get away with it, to be honest, but
we'll keep trying to get away with it.
Yeah.
See what happens.
Yeah. All right.
Thanks, Fred.
I'll see you next time.
Soon.
Cheers.
Bye-bye. Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio, who turned up for 2 episodes this week, which is good because we had 2 episodes. And from me, Andrew Dunkley, thanks for your company as always. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.